Welcome in dot core. In quantum mechanics, photons can briefly collide in a rare phenomenon called light-by-light scattering, influencing the muon's anomalous magnetic moment, muon -2. This has puzzled scientists with experimental results not matching predictions, suggesting possible new particles or gaps in calculations. Researchers at 2Y now show that tensor mesons, short-lived spin-2 particles, play a significant role in light-by-light scattering. Their advanced holographic QCD approach refines its prediction for muon GUS2, helping us determine if a discrepancy points to new physics or deeper understanding of the standard model. Keep watching this video to learn more about this topic. The discovery event the muon's anomalous magnetic moment written as a mu equals G minus 2 mu 2 serves as a precision test of the standard model. Muons, heavier cousins of electrons, act like tiny spinning magnets. Their magnetic behavior is influenced by every particle they can interact with even virtually. This makes their wobble an extremely sensitive probe of quantum physics. For decades, this number has been at the center of a mystery. Experiments at Brookhaven National Laboratory and more recently Fermi Lab measured AMU with extraordinary precision. Their results showed a small but persistent gap compared to standard model predictions, large enough to raise a possibility of undiscovered physics, but small enough that theoretical uncertainties could be to blame. One of the most challenging pieces of this calculation involved hydronic light by light HLBL scattering, a process where photons interact by producing virtual particles like quark-antiquark pairs. These interactions are subtle but complex, requiring models of the strong nuclear force energies where standard computational methods struggle. Previously, models included contribution from meson composite particles made of a quark and antiquark, but tensor meson were treated with heavy simplifications and assumed to have little influence. This assumption has now been overturned. Jonas Moore and Anton Reban at Tuween used holographic QCD-HQCD, a technique inspired by string theory to re-evaluate the role of these particles. By mapping complex four-dimensional interactions into a five-dimensional gravitational model, they could better capture the behavior of tensor meson in photon scattering. Twins analysis shows tensor meson have a greater impact on light-by-light scattering, especially at low photon energies, and even reverse sign in some cases. This new insight aligns with experimental data reshaping the muon G2 puzzle. Scientific importance and theories. This work addresses one of the largest uncertainties in the muon G2 prediction, the symmetric longitudinal short-distance constraint. In earlier models, this condition was only about 81% satisfied using axial vector mesons. By incorporating a full tower of tensor mesons, the TU-Wien team closed this gap completely. That's no small achievement. HLBL scattering has long been a source of frustration for theorists because it involves a strong nuclear force in a regime where no single method works perfectly. Perturbative QCD, which handles very high energy interactions well, fails at these intermediate scales. Dispersive approaches, which use experimental data to constrain the calculation, can't capture all of the underlying physics on their own. Holographic QCD offers a powerful workaround. By translating the problem into a five-dimensional space, physicists can use tools from gravitational physics like Einstein's equations to model meson interactions. While this approach is unconventional, it has proven remarkably effective for modeling the dynamics of strongly interacting particles. Including tensor mesons doesn't just improve the internal consistency of these models. It also strengthens their agreement with real-world data. The updated calculations line up well with measurements from the Bell experiment and match recent dispersive evaluations which examine photon-photon scattering in detail. The timing of this refinement is particularly important. Fermi Lab's latest muon G2 measurement released in 2025 held the experimental uncertainty from 22 by 10 minus the first to about 11 by 10, the first. As experiments become more precise, theoretical predictions must keep pace. If a discrepancy between theory and experiment remains after these updates, it will carry more weight, making the case for new physics stronger. If the gap narrows or disappears, it suggests that improved calculations like this one may resolve the anomaly within the standard model. Implications and what's next. The implications of this work extend beyond a single calculation. First, it allows physicists to interpret Fermi-Lab's G2 results with more confidence. A closer match between theory and experiment would strengthen the standard model, while a persistent gap would sharpen the case for new particles or forces. Either outcome provides a clearer picture than before. Second, This study emphasizes the value of collaboration between theoretical and experimental approaches. Future work will likely involve Lattice QCD teams incorporating tensor Meson contributions, dispersive analysts refining their models with this new input, and experimentalists at facilities like Bell continuing to provide precise data on Meson behavior. This multi-pronged effort will help further reduce uncertainties. Third, the use of holographic QCD underscores the importance of creative problem solving in physics. By borrowing concepts from higher dimensional theories, researchers can make progress on problems that once seemed intractable. This approach could inspire similar strategies for tackling other unresolved questions in quantum chromodynamics and beyond. Finally, the study serves as a reminder of the profound influence of virtual particles. Though they exist only momentarily, their effects ripple into measurable quantities like the muon's magnetic moment. Studying these effects gives us a rare window into the quantum vacuum and possibly the physics that lies beyond our current models. Looking ahead, expect refinements in HLBL calculations, expanded lattice simulations, and even tighter experimental constraints. Each improvement will make the muon G2 value an even sharper probe for testing the limits of the standard model. Outro 2 was discovery of tensor meons in light-by-light scattering advances our understanding of the muon's magnetic moment. Using holographic QCD, they reduce a key uncertainty in the calculation, offering a clearer foundation for interpreting future experimental results. Will the muon GUS2 anomaly reveal new physics? Stay tuned for more breakthroughs in particle physics. Thanks for watching. Call.